right. Hello, everyone. Okay, so this talk is going to be kind of a origin story talk, which I think has already been alluded to. So it'll be sort of like Batman Begins for distributed commit logs, but maybe less exciting. So as Alexi said, I'm coming out of a company, LinkedIn, where I worked on Kafka for a long time. One of the reasons I like to talk about the origin for any system I'm involved in is I think it tells you a lot about the problems people are trying to solve, why it is the way it is, how everything turned out, and then also where it's going, right? There's usually some whole mindset which is embedded in any of these technologies, and if you kind of understand that mindset, then I think you can kind of understand what the technology is really about. And so that's the purpose of this talk. Hopefully it'll be useful even to people who have some knowledge of Kafka already or using it. Hopefully it'll add a little bit to your understanding. So I think we started working on Kafka, or this story starts roughly in 2009. I was on the data infrastructure team, and I was responsible for a lot of the Hadoop rollout. I'd previously had sort of a promiscuous relationship with different open source projects and had done like a distributed key value store and other things in the company. The thing we were really trying to do was get a complete copy of everything happening in the company in Hadoop. We had also like a relational data warehouse, which was Oracle at the time and became Teradata later. So this is that kind of data lake vision of having a complete representation. We didn't have Spark at that time just because I think it didn't exist. But that was really the goal we were centered around, and this turned out to be much harder than I thought. And so we had planned to spend a few weeks on getting data into the cluster and then spend a lot of time on processing and fancy algorithms that would exploit this. And of course, like I think as a lot of people have found, the plumbing problem is still not 100% solved. So then we spent more and more iterations on that. Our initial attempt in that area was really to just kind of gut it out, like just do integration with different systems, get it into some kind of good form in the Hadoop cluster, and then hopefully that would solve the problem. And the feeling was if we just worked really hard at this, we could like get through it. And I feel like a lot of the work in like ETL or data plumbing has had that mentality, as if you just get enough people and they all just like write enough scripts, then it will be a solved problem. And it turned out that really wasn't solving the problem. After spending a fair amount of time on that approach, we realized like we had about 14% of what was really happening in the business. Like we did some kind of, let's write down a list of everything happening in the business and let's try and figure out what percentage we actually have a representation of. And we were really only solving the problem for Hadoop. There was a bunch of other systems in the company. We had graph databases and search clusters and a relational data warehouse. And everything we did for Hadoop was really one-off for Hadoop. So, and so the kind of problems we had, like the data coverage problem was one, just like the many integrations with different systems, dealing with like messes of data formats. And then probably the biggest one was just, the whole company was changing all the time. It was evolving. People were writing new code, and keeping up with all that change was a big challenge. And so this kind of led me out of this area of infrastructure, which is always solving these well-defined problems and building, core abstractions, and into this area of like data and how it flows in a company and what that is all about. And so I spent a fair amount of time just doing a inventory of what was happening at LinkedIn, what was happening at other companies, how did they solve these types of problems, what things worked well, what didn't work. So this was the state of data flow at LinkedIn in roughly 2009. It's not super pretty, and it got better. So, but I think it's worth just going through what was happening and what were the problems with those. So we had a bunch of different types of data. We had like data in databases, which is probably what many people would think of as all the data, but it wasn't the only thing for us. We had relational databases where there was multiple mechanisms for getting data. There was like real-time polling for changes. There was like a log replication. There was like CSV dumps. These all happened on like different latency scales. Some were fast, some were high throughput. There was also like key value stores, and we had some mechanisms to kind of shovel data in and out of them. But for a web company, there was other stuff. There was user events, and by events, I mean kind of like logs. I mean like what's happening in the business, like what are people clicking on, what are they searching, what's happening. And I think for a web company, this tends to be the kind of like clicks, impressions, joins, searches, but every company has this type of data, and it is kind of a core thing which is a little bit neglected by data infrastructure, right? This is what is the business doing? And so, in a different type of business, it might be stock trades and stock ticks and market information and that type of stuff, right? But for a web company, it's going to be clicks and impressions. And our approach to this was pretty low tech at the time, which is, I think we copied all the logs to one place, and at the end of the day, we basically like rsynced them over and loaded them. And usually whenever you see rsync in some system diagram that's supposed to be highly reliable and robust and the critical foundation for many other things, usually there's going to be some pain. So we also had, and I should mention that was like a purely offline thing. At the end of the day, data got copied over, and it really was only available to the data warehouse and then to Hadoop by some egregious hack. And then finally, we had these kind of like logs and operational like app metrics, like JAMX stats and Unix stats. And those were kind of very real time, but only available in limited systems. And then we had kind of a bunch of different messaging things, primarily ActiveMQ, but they were just kind of here and there. Like some application would have a messaging setup, and some other application would have a messaging setup, and there was nothing shared between these, and it was really just a way for that application to kind of talk to itself. And so each of these things, like they kind of made some sense taken on their own. A few of them were really bad, but mostly on their own they kind of made some sense. But when you put them together, it was really kind of a big mess. So it was something like this, but actually much more complicated, right? So in reality, there was hundreds of databases. There was about 300 individual services. This was replicated over a number of data centers. And so you can imagine just like going into the multi-data center world was pretty awful if you think about how data flows and how that had to be like improved. And as each of these kind of pipelines grew with the company, it just had its own problem. So we were basically solving this scaling problem over and over again. And then the team I was running that was in part focused on this Hadoop project, we were basically having to scale up to handle all these different data sources and integrate with these different things. And the reality was we just didn't cover a lot of what was in the business. And so that was totally unavailable for analytic processing whatsoever. And when we did cover something, it was a bunch of manual work, and it was boring to do, and it was hard to keep it working. And so coming from an infrastructure background, I guess you always hit a problem with the mental hammer that you understand. I was looking for an infrastructure solution. An infrastructure solution is usually one where you spend a lot of work up front and then very little incremental work on each individual problem. So I wanted it to be the case that we could kind of cover a lot of what was happening in the company without this kind of like gutted out, really hard, data set at a time, like almost consulting team we would have to build to do it otherwise. And so the thought process we went through was really take all these different types of data and all these ways of shipping data and see if there was some kind of common infrastructural pattern. And the idea we came up with was trying to represent this stuff as streams. That a stream is really actually a good core abstraction for data in a business. You could think of clicks on a website as a stream of click events. You could think of log files as a stream of log activities. You can think of changes coming into a database, and this one's a little weird for people, but it's actually a really powerful representation. So you can think of changes coming into a database as a stream of updates or final states to that database. And you could actually think of the integration with online systems, like how do you feed a search cluster, or how do you feed a replica database, or how do you feed a cache. You could think of that as something that subscribes to that stream and like indexes it in some way. But you could also have like applications that tap into these streams and give you some kind of analytics on them. And you could think of like this whole warehouse analytical world, the kind of data warehouse area, broadly speaking, which might include Hadoop and relational data warehouses or Redshift or all kinds of technologies. You could think of that as another subscriber, maybe on a slightly slower time frame. And being able to come up with something that would act as that hub and would actually interconnect things on these different time frames, that was really the first goal. The second goal was to support this area of things that would kind of plug in and process in real time, because usually your goal isn't just to get something from point A to point B. It's usually to get it from point A, combine it with things from point B, C, and D, do something with it, and then get it to point D. Okay, so that was the problem we wanted to solve, and this is what we started out thinking about. We set out to solve this problem really with off-the-shelf messaging systems. We were running primarily ActiveMQ at that time. We were interested in running RabbitMQ because it was written in Erlang, and we thought that would be cooler. And we thought, look, we didn't know anything about messaging systems. It was basically a team of people who'd worked on distributed databases. But we thought, well, this is clearly a solved problem. These systems have been around for a long time. So we'll try and use them. And maybe they don't have like a perfect distributed setup, but maybe you could build some kind of sharding layer on top, like the equivalent of sharded MySQL. And we could build our stream data platform that would hold all this streaming data on top of these systems. So we tried that. And it didn't go great. So we spent a chunk of time on that project, and we found that it was just basically a terrible fit for what we were trying to do. So for these high volume log and activity and metric streams, the throughput was just not sufficient. The integration with batch systems like Hadoop was not good enough, primarily because the way these messaging systems handled persistence was not good enough. So if you brought down your Hadoop cluster for maintenance and brought it back up a few hours later, you were effectively storing the entire activity stream of a very large consumer scale website during that time period. And the messaging systems were not meant to do that. They would have this very small buffer, and when that filled up, they would basically back pressure. But you can't back pressure your users and be like, come back later, we can't log your stuff. So that didn't work. Finally, they were a pretty poor basis for stream processing, for any kind of richer application integration that doesn't just process a single message at a time. And the reason for that is a little bit involved, so I won't go into it in great detail, but I'll touch on it. The kind of ordering guarantees were not very strong, and that was a big problem for and indeed, the delivery guarantees in general, and that was a big problem for any kind of important database changes. So if you have a search cluster that's indexing data coming out of databases, it's very important that that search cluster end up with the same stuff that was in the source database. If you rearrange the updates out of order, and maybe you update your account twice, and the second update comes in first, and the first update comes in second, then the search cluster is not represent, it's permanently out of sync, and that's probably not going to work. And so getting things in the right order and not losing updates was pretty important. And then being able to partition and scale this out was really important. So that kind of led to our second attempt at this problem, which was to build Kafka. This is our kind of reinvent the wheel approach. And naturally, we gave the same time estimate that all engineers give when they don't know how long something will take, which is 3 months. And we're still working on it, so that was wrong. But we did have something out in roughly 5 months that worked, and then there was a lot more to do to make it better over time. And so I'll give kind of a 30-second overview of Kafka. I think a lot of people in this audience probably know that. At heart, it works like a messaging system. There's a cluster. You produce messages into it. There's consumers who subscribe to those. Internally, it's really different. So it doesn't really work at all like an ActiveMQ or whatever. Internally, what it's maintaining is a log of changes. And this log is, each of these rectangles is meant to represent a record. And records are kind of occurring over time. And the old records are on the left, and the new records are on the right, although I guess that's just a convention. Writes always go on the end. You don't change the old stuff. And readers are always at some position in this log, going from left to right. And so this abstraction is almost too simple to even be worth talking about. But it turns out to be really powerful. So first of all, you can treat it like, you can use it for batch processing. Something can start at 0 and process really fast to the end. And so you can actually do batch processing right off of the log. You can also subscribe to it in real time and treat it like a messaging system. And you can do anything in between. So you could have a Hadoop cluster where you replicate data to it into HDFS, mostly in real time. But if the Hadoop cluster goes down, then that reader is kind of stuck at its position. When it comes back up, it catches up pretty quickly. And so it's kind of nice that you have this control over where you're at. It also turns out to be a really good basis for publish-subscribe messaging, which is not obvious. But if you think about two systems or applications, maybe one of these is a application, one is a Hadoop cluster or something, they're each at one of these records. And I've kind of given each record some kind of logical number. In Kafka terminology, this is offset. And you can kind of reason about the state of this system, at least for this partition of data, by what offset it's read up to. So in some sense, this system is at time 7 or offset 7, and this is at time 11 or offset 11. And so you can kind of reason about how these different parts of your company are progressing forward in time as they replicate these changes. And that's pretty much everything there is to know about Kafka, except that if you take a bunch of these and you put them together, that's basically a Kafka topic. And a topic is one of these feeds of data. And so these partitions are internally replicated for fault tolerance. When you write, you're writing to a leader, which replicates to followers, and then it tells you your message is committed. When it's committed, we guarantee you it won't be lost if the leader fails. And so each of these kind of logs is fault tolerant. And then they're spread over a cluster to kind of scale out the amount of data that's handled. And so our goal was really to be able to combine these different use cases. And that kind of came up with these different things you have to really achieve to make that work. So for logs or operational data, you really have to have scalability, which is kind of comparable to a file system. Maybe you're not quite as good, but you should be not too much worse, or it's not really going to fly. And so that means really hundreds of megabytes per second per server in throughput, and being able to store lots of this log data per server. And this was really kind of where a lot of the messaging systems fell down, was actually on both of these dimensions. You need to be able to provide strong guarantees so that you're not losing data in flight between things. There's definitely some uses, like some monitoring systems are OK with a lossy pipeline maybe, but a lot of use cases actually aren't. And so if you can't hit this, you basically aren't going to be able to handle a lot of use cases. And then finally, we personally wanted something that was distributed by default, so something that was built to run as a cluster, something that you would think about as a cluster. When you wrote, you wouldn't think about, oh, I'm writing to machine, XYZ123. You would think about, I'm writing to the cluster, and presumably there's some nodes that are handling these writes. And I think if you get that right, it actually allows everybody to operate at a much higher level of abstraction than if you really have something that feels like a collection of nodes that you interact with and manually configure things for. So this was our goal, to be able to unify these different pipelines. And I think we did. We at least hit those requirements. And so this kind of stream data platform idea, we ended up building it using Kafka. It took a fair amount of time at LinkedIn. We moved each of these use cases over one at a time, so user events, and then logs and operational stats, and then database changes, and then a lot of different application-specific messaging and processing things that would kind of show up in this area, and the whole kind of offline pipeline. And at that point, we started to focus on our second idea, which originally was more of a hypothesis. It was like a venture bet, which was that this stream processing area would actually be interesting or important, and that if we captured a bunch of data as real-time streams, it would be useful to process it as real-time streams. And as you can see in that picture before, a lot of data was not available as a real-time stream, and if data is not available as a real-time stream, you don't process it as a real-time stream. So if you have data only via some kind of nightly CSV dump, then you're going to process the nightly CSV dump at the end of the night. And this is something which is very obvious, but is actually often missed, which is, if your data collection is batch-oriented, then your processing is going to be batch-oriented. If your data collection is streaming, in some sense, your processing may be streaming, it may not be, that's up to you. And so, we believed that if we somehow made the entire set of everything happening in the business available as a stream, people would use that. And it turned out that was true. The example I use to illustrate this is the US Census. If you know how the US Census works, I think the program is in the US Constitution, if I'm correct. And it works by basically every 10 years you kind of walk around to each house and you count the number of people in each house, and then you add up all those counts, and that is the total number of people. That is obviously a very batch process. The streaming equivalent of that is going to be journaling births and deaths. And so if you journal births and deaths, then you know how many people there are in the country, not every 10 years, but continuously. But more interestingly, you actually know how many people were in the country at every previous point in time, which is kind of an interesting observation. Rather than just knowing every 10 years, you actually know at every point in time the state of the world. And this kind of understanding actually led us to realize that stream processing is a very general thing. When you talk to people about it who are aware of kind of this current state of the world with stream processing systems, they often think it's this kind of weird, lossy, thing that just fits in a little niche. And it kind of doesn't get the right answer, but it's faster. And the batch systems get the right answer, but they're slower, and that's the trade-off. That is probably a correct statement about a lot of the current state-of-the-art systems, but is not a correct statement about what's possible in this area. And this area is moving real fast. And so you kind of want to root yourself in what's possible in the area. And what I would say is actually these stream processing systems are actually potentially a generalization of a lot of what people do in batch processing. And if you're aware, a lot of what happens in the back end of companies is basically big batch jobs that turn over once a day. I mean, that's how a lot of corporate America works. And if you haven't ever peered under the covers, I can tell you it's true. So the way to understand this kind of idea that it's a generalization is, most people are familiar with request response processing. This is your classic client-server thing. There's a REST service. You give a request to a service. It gives you back a response. For every request, there's a response. It does it really quickly, or maybe it times out your request. Batch processing, I think everybody knows. This is, you have the big table with all the data. You do a big scan and compute something. And so you kind of take all the inputs, and you give all the outputs, right? And stream processing is just if you give a knob that goes between all inputs, all outputs, and one input, one output, and you let the program itself control that. So the program kind of operates continuously and controls what's output. And it turns out that a lot of what people think are restrictions on this area are actually just restrictions on the current technology, and the technology is getting better real fast. And so I think this is a very exciting area. There's actually a really great O'Reilly blog post on this by one of the people working on Google Dataflow, which is one of the good stream processing systems. So if you're interested in that whole idea around stream processing, you can go check that out. I think it was posted in the last week, roughly. So what does Kafka have to do with stream processing? Well, I said you have to get some kind of stream of data to be able to process it. But the way you can think about stream processing in Kafka is kind of like Unix pipes, right? So anybody who's used Unix is kind of familiar with these pipes. You can kind of take any program, you can throw a pipe down, and you can pipe it to any other Unix program, and you can chain a lot of these together. That was obviously a fantastic integration mechanism for the days where everybody logged into a central computer, and there was just the one. Probably in the modern world, there's, programs are, first of all, distributed. They run continuously. And so they are going to communicate over a network. It's a little different than what you need out of Unix pipes. But the concept is the same, which is you can have these transformations which take these streams or continuous feeds, do some kind of magic. Maybe they're taking two different feeds and joining them together. Maybe they're aggregating. Maybe they're filtering. Maybe they're transforming. And they publish out new feeds. And you can have lots of these. In some sense, this transformation is just code. There's a bunch of frameworks, though, that will make that type of transformation a lot easier. So the relationship between Kafka and these frameworks is kind of like Kafka is in some sense giving you streams. These frameworks are in some sense giving you processing. And together, I guess you would have stream processing. This is my math formula. So what are the frameworks? There's a bunch of them. Storm was probably one of the most popular earlier on. Spark streaming is really popular now and it's super awesome. There's one that came out of LinkedIn called Samza. There's actually not represented on this slide. There's a system called Flink. All of these actually integrate pretty well with Kafka and are really commonly used with Kafka. OK, so if you put that together, if you put together the stream processing with a lot of the other things in that kind of stream data platform picture, this is the type of architecture you end up with. This is what we ended up with. I'll illustrate a few things about how this works. So first of all, we could capture a lot of what was happening in these applications in the business coming out of databases, and that would all kind of go into this central Kafka cluster. In reality, this picture, of course, is more complicated than any, as all architecture diagrams are. They hide things. So this would be replicated across data centers, and this stuff was all in its own analytical data centers. But I'm kind of showing the idea rather than the complex reality. So, in this kind of central platform, you could replicate all these different types of changes: monitoring data, database data, event data. You could take anything that ended up here, and you could transform it into new stuff. And that new stuff would look like a Kafka topic, just like the original stuff. So from the point of view of the subscriber, they don't know who's sending the stuff. They don't know whether it's like original stuff coming out of an application or some transformed thing. And then that fed two things. So first of all, a lot of these real-time processing things would feed back into the site. So it would go back into some database for real-time serving. That was super common. It would go into some kind of user-facing thing. So like if you go to the LinkedIn homepage, there's a whole bunch of updates about your network. In some sense, that's a big real-time processing flow on top of these update events that are coming out. That's a kind of news feed on the homepage. It also fed this really rich set of like real-time analytic capabilities. And this turned out to be a collection of systems rather than a single system. So the whole security and fraud area was basically a big Kafka processing area. This is detecting any kind of bad things, abuse, spam, scraping, whatever kind of abusive things people are doing. A lot of our real-time analytics and monitoring was in that domain, right? So these were all systems that would take these changes, replicate them into some kind of store, so some kind of time series store or some kind of search store. And then you could do different types of queries. So you could do like log search, or we had a fantastically cool application that took all the different calls to services in the real-time stack, all the errors that occurred anywhere in the business, and all the information about the devices in the data center. And it basically did like a giant distributed join against all of these. And then you could compute like for each user request, what machines did it hit, what services did it call, and then how much those machines cost. And then you could say, well, if this machine costs $2,000, that would divide up over all these requests. And so you could say, well, the cost of this page view was this, and the cost of this page view was this. It was pretty cool. And all of that actually kind of sprung up in an unintended way, in that we knew we needed to get stuff between these things. We knew we needed to get stuff in this area, but we didn't really realize like how much there was in this intermediate area. So this kind of started out nascent, like it was more just like a pipeline, and it turned into a whole platform. It was cool. And so that platform ended up getting used at pretty fantastic scale. So over 1 trillion messages written per day. Since each one of these feeds is multi-subscriber, any write you do is probably going to at least Hadoop and at least a few other things. A fairly large amount of data in the Kafka clusters. And this is kind of the backbone for a lot of the data stores, like how data got into search, how it got into the social graph, that news feed kind of homepage. And they're actually working on making this the kind of commit log for the primary distributed key value store, which is a pretty cool project that LinkedIn is doing. And it became the basis for all that type of stream processing. So that was the journey at LinkedIn. It turned out LinkedIn wasn't the only person using this. We open sourced it, as I guess you guys know, since a lot of you guys are using it. And it's become pretty common across a lot of big internet companies, also a lot of enterprises outside the kind of Silicon Valley crowd, which has been very exciting to us. And about 9 months ago, the team at LinkedIn left, and we decided to start a company around this. We felt this kind of view of data as a continuous stream and having some platform you could plug everything into, that was actually a big deal. It was certainly the biggest thing I saw come out of the kind of infrastructure area in my time there. And we felt like, hey, this is something a lot of people could benefit from. But it's not something that's going to kind of build itself. It probably requires a little bit of help. And so the company's been around for 9 months. We're basically kind of putting together the rest of the platform I felt LinkedIn had beyond just Apache Kafka, as well as doing a ton of Kafka development to get all the security features and make the management of the cluster easier and all that kind of stuff. If you're interested in this area, there's a number of resources that have more information. I realize this is kind of a light, breezy overview. So we have a blog at Confluent, which has just a ton of writing around streams and streaming data. So you could probably spend several days just reading these blog posts. In particular, there's a blog post we did which was just on this stream data platform concept, which is like having a central platform for streaming data and how that works, and a lot of the like practical aspects of how to do that. Whereas this talk was more brief overview. So you can check that out. There was a long blog post on this log concept, which O'Reilly wrapped up as a book. And there's a ton of Apache Kafka resources here, and like everything's on Twitter, of course. And that's it. So thank you very much.